We're going to solve a differential equation in a really trivial case. In fact, so trivial that you wouldn't ever do it using differential equations. So why do it? Well, so that we can concentrate on what's really going on and the meaning of it rather than getting bogged down in the calculation. So here's the motion of the car from section 1 when we looked at rates of change. We've left off the numbers on the axes from the displacement and velocity time graphs so that we only have values for the acceleration. Let's ask the question, how far does the car go in the 10 seconds? In other words, what's this value on the displacement axis here? Now first we can use the area under the acceleration time graph to give information about the velocity by integrating the acceleration, and then we'll integrate the velocity to get the displacement. This is a general feature of differential equations. The acceleration is the second derivative of displacement, so we should expect to have to integrate twice to get back to displacement. So let's have a go. The acceleration is the rate of change of velocity, so we'll get velocity by integrating acceleration. And we're going to do it in two different ways to illustrate the difference between indefinite and definite integrals. Let's do the indefinite integral version first. So here we have an expression for the velocity where we have taken a value of a constant value of 2 for the acceleration, and when we perform that integration we get 2t plus the constant of integration. Now we know that at time 0 the velocity is 0. So this is 0 when that is 0, meaning that c must be 0. So for the first part of the motion, v is equal to 2t, and when t equals 4, the velocity is 2 lots of 4 is 8 meters per second. So we can put the 8 on the velocity time graph. Alternatively, we could take a definite integral approach by putting the boundary values of 0 and 4 on the integral. Then just like before, we can take a value of 2 for the acceleration, integrate between the two boundary values, and we get 8 minus 0, which gives us the 8 that can go on the velocity axis. Now let's find the area under the velocity time graph, which will be the distance travelled, as the sum of two integrals, one from 0 to 4 seconds and one from 4 to 10 seconds. These are the functions describing the velocity in the two stages of the motion, and they give us the sum of two integrals for the total distance travelled at 10 seconds. The first deals with the motion from 0 to 4 seconds, and the second deals with the motion from 4 to 10 seconds. We'll only do a definite integral approach here, but you could put in boundary conditions like we did before. If we do the integrating, 2t turns into t squared, and 8 turns into 8t, and substituting in the boundary values gives us these numbers here. 16 meters is the distance travelled in the first stage of the motion, and 48 meters travelled in the second stage of the motion, giving an answer of 64 meters, which we actually knew from section 1, but it was worth doing this way just to show how it all ties up. So the answer to the problem is 64 meters. Now we could have worked that out by adding the area of the triangle in the velocity time graph to the area of the rectangle, and in fact that's what we did in section 1. But we could only do that in section 1 because our example is simple enough that you can draw it as a triangle and a rectangle. The method of integrating is far more general, and it's more general in two important ways. Firstly, it can deal with more complicated functions where the shapes of the graph are not easy to deal with geometrically. And secondly, the integration approach gives general solutions for any value of time, not just the 10-second value of time. So let's see if we can find a general solution in this case for displacement as a function of time. Well, up to 4 seconds we have t squared from here, And beyond 4 seconds, we have an initial 16 meters from the first stage of the motion as, if you like, a head start. And then we have 8 multiplied by the time elapsed, but it's the time elapsed after 4 seconds, so the time elapsed in the second stage of the motion. So that's why here we have 8 multiplied by, and this is a shifted time axis if you like, so it's the time elapsed in the second part of the motion.